Now that we're getting the hang of percent efficiency, let's go ahead and try a different kind of example. So let's go ahead and work with a third class lever. And the reason why a third class lever is different is because the third class lever always has a mechanical advantage less than 1. So let's go ahead and see how that affects our percent efficiency equation differently, if it does at all. So a third class lever has our force effort on the inside. So we'll go ahead and say FE. And let's go ahead and say we're applying an effort force of 50 pounds. And let's say we're using that 50 pounds to lift up a force resistance of, let's say, 15 pounds. And you might say, well, why are we applying so much effort to lift something so light? And that is because, remember, that a third class lever, or any machine with a mechanical advantage less than 1, you give up force, you apply more force than needed to give you a huge distance advantage. But let's go ahead and say that our effort force is 2 feet from our fulcrum. In other words, this is our distance effort, if you look at it. The distance from our effort force to our fulcrum. And let's say our force resistance to our fulcrum, let's just go ahead and keep this simple. Let's call it 5 feet. And so what would be the percent efficiency? And the first thing we need is our AMA, and we're just going to go ahead and reuse this equation, our AMA-free equation. So we'll put FR on top, and FR is, of course, 15 pounds. And on bottom, we'll put our force effort, our 50 pounds. And I'll go ahead and set this equal to our AMA. And that color coding was bothering me. But anyway, what's 15 divided by 50? What we get is 0.3. And so we'll say, well, pounds cancels out, and we get 15 divided by 50 is 0.3. And of course, then we'll solve for our IMA. Well, our IMA is just our I'm a deer equation, so we can just reuse that again. No reason to rewrite it on this page. And so DE is, of course, 2 feet, and DR is 5 feet. And 2 divided by 5, let's pull out our handy-dandy calculator again. What's 2 divided by 5? And we get 0.4. So equals 0.4. And you might say, well, why is mechanical advantage less than 1? But hopefully by now that should be incredibly obvious. Mechanical advantage less than 1 means you have a distance advantage, which is what's happening. I'm applying an effort force here, and that will lift up this bar a certain distance, but at this end, this 15 pounds will go way further away off the page. But with that, we have everything we need to solve for our percent efficiency. So let's go ahead and write out our equation. We'll write our big parentheses and our little divided by. And on top, we can go ahead and put 0.3. And on bottom, we can put our IMA, which is 0.4. And then, of course, we'll multiply that by 100. And we'll go ahead and plug this into our calculator. So we'll hit our parentheses button, and then we'll type in our numerator over denominator, and we'll put 0.3 on top. And on bottom, we'll put 0.4. And then we can close out a parentheses and just type 100, just like it's written here. And we get percent efficiency equals 75%, meaning we're losing about a quarter or 25% of our energy or our work due to this system, due to the inefficiency of this system. And as you can see, that it doesn't vary very much at all. It doesn't make that big of a difference at all to have a mechanical advantage less than 1. You still get the same values, just now less than 1. You still get a percentage that makes sense.